Voglio iniziare la presentazione. Sì.
In Portogallo c'erano 15 minuti e 20 minuti.
So before the seminar of today, just announcement of few new people who have arrived recently. Miguel Ángel Escalona, who's going to be working for PhD with Claudio, which is not here, and Pablo Creuquín has also arrived here, and we'll be working with Jose and myself and Victor also for his PhD. So welcome.
So, this is someone coming, but let's start. And
so I classic.
Let's
make
go
some
back
darkness in the room because then it's
because
the
the slides are almost in dark. So, well, I mean, first it's my pleasure to welcome Santo, Santo Fortunato, because we have been colleagues for quite a while. Yes, but yes, I don't have the minutes, but okay. I know more about that. So he got his PhD in Bielefeld in Germany, and then continued there as a postdoc for years, mostly working in topics that are more like field theory and things like that. I read the paper from that time. It was really weird after. No, then he moved to Indiana University in Alessandro Sospiniani's group, where he started to work in these topics more related to complexity. And from there to Torino, where he's now a research scientist and is leading one of the areas of the IFISC Foundation. This is where we met actually, because I was also there for a while. He has also been invited professor in several universities, like in Massilia or in Paris. And well, he has a lot of papers. But there are two that are, in particular, say, central because they are reviews, and I think in both cases they are like the first reviews in the two areas. So one in community detection and the other in social modeling from the physics perspective. Yeah, because social modeling is quite much of it. So I think this is the kind of thing that he will talk about, and I will just welcome him.
So muchas gracias. So I must say I feel very comfortable here because I am Italian, yes, but I come from another island of the Mediterranean Sea, which is Sicily. A little bigger than Mallorca, but still very comfortable. A lot of sea, a lot of actually more fishing here. Apparently, that's not very. And also feel comfortable, of course, because I know some people here. Jose, with whom I was colleague at the same institute for 4 years. Of course, Maxi, I met several years ago, and I read a few times. Emilio, Raul, Victor, so I feel very comfortable. But since I know that they are not the only people working here, so the goal of today's seminar is to give you some brief highlights of the work I've done in complexity, because before I was a particle physicist, so that's probably not interesting for you. And I don't remember much of what I did anymore, it's been a while.
It's good to forget something.
Yeah, yes, in a sense. I wish I could have done it earlier. So for the people who are not actively working in this area. So you may know some of the main concepts, and I will tell you what I'm mostly interested in, and then put things in a somewhat broader perspective. So this is the outline. So a brief description of the research topics, and then some highlights, especially my work in community detection and social dynamics, statistical physics modeling and social dynamics. So topics can be divided in 3 areas in my case. There is some interest in networks, which is divided in 2 subcategories. Analysis, so in this case really data mining and description of what really happens of several types of networks. Social networks is a network of people talking on the phone, mobile phone. In Belgium, yellow is French, red is Flemish. So you see that they form quite linguistically homogeneous communities, not so many links within them. This is a zoom in. You see these small communities in the middle. It's also a mix of green and red. This is information network. This was actually the very first thing that I started to do when I moved to Indiana University in 2005. This is a piece of the web, the website of the Chicago Tribune, famous newspaper, and then it's the domain www.chicagotribune.com, and then there are all the domains inside. And this is a citation network of network scientists. So each of these balls represent guys fairly visible within the area of complexity in networks, like Barabasi, or Alessandro Vespignani, Romualdo Passos-Torres, Recalde, and so on. The bigger, the more citations they get from other scientists. So each arrow, which is directed, indicates how many times the guy has cited the other guy in his work. So of course there are bigger arrows, meaning that there is a big flux of people that regularly cite the same type of people. And the size of the ball indicates, it's a logarithmic scale in this case, how visible the guy is within this network. So in this area, I analyze these systems to discover their properties and to try to model their origin and their evolution, possibly, to see what we can do. The other area is more methodological. It has to do with the problem of finding clusters in graph. Graphs look pretty much like this, like complex networks, let's say, which means that there are some groups of nodes which have similar properties. They are somehow related because they have the same function or they are similar to each other, like actually people. And in a network, you see this because that means that these nodes are very tightly linked to each other. Like in this case, this is of course a very schematic example. It doesn't correspond to anything real. It's also very small. And the thing is, the goal is to identify this group of nodes because this gives you additional information about the system, which will be very large, millions of nodes, about this internal organization, which parts belong together, which parts are somehow self-organized in a more consistent way. So today I will say something about results that I did in this area here. It's community detection. Then the other thing is the statistical physics modeling of social dynamics. And the path is the usual one in statistical physics. You start from disorder and you try to move to order. People thinking in a different way, people having the same opinion at the end of a discussion. People speaking different languages, people speaking the same language. It can be the one of any of them or something new that they somehow rearrange. So the usual pattern, the way statistical physicists look at these things is that there are local interactions in which people basically interact only with their local partners, the guys that they're really in contact with, which is just a very, very small part of the whole system. And this local interaction through mechanism of imitation, adaptation, so-called also peer pressure, leads to homogenization and possibly to a global order. It can be consensus, can be a common language, it can be a common culture, it can be collective motion, formation of hierarchies, and these kind of things in society. So from disorder to order. We're used to do these things, but of course in society it's a little more complicated. If you want to know something more from a popular science point of view, you may want to take a look at this very nice book written by Mark Buchanan, The Social Atom, which is also a very interesting subtitle, saying why the rich gets richer, cheats get caught, and your neighbor usually looks like you. So this is very interesting book, and it can be read in a few hours. Gives a lot of examples also from economic physics, not only from social dynamics, and also some historical background. Showing, most importantly, this is a very old idea. It dates back to Hobbes, and then after him, Condorcet, Quetelet, Comte. There's been some kind of evolution in philosophy also about this idea that societies have rules which are strict. In fact, at that time they were believing like mathematical and precise, like the one of Newton, they were so impressive to describe the motion of the stars. There should be something similar for society. Very, very thin. Now, it's not thinking like this, but in some cases, in some dimension, which is a collective dimension, when it comes really to statistical distribution, for several social phenomena, it's possible to do a quantitative investigation of this kind. And what I've done here in the last few years was to try to make it a little more quantitative, somehow to study empirically phenomena for which there were data, and try to formulate or discover simple relationships or simple distributions, things like scaling and universality, in distributions of things which have to do with social phenomena. I will show you two examples from elections, so voting behavior and citations. So behavior of people citing each other in scientific publication like everybody is doing today. If you had such a simple description of reality with this very simple, nice striking signature, simple distribution which are regular, which have a simple shape and so on, you can attempt a simple modeling trying, like the way we're used to, trying to explain what you see in a simple way without paying attention to the details. Last but not least, since I started just a couple of years ago, science of science. Studying basically you, no? As you write your papers, as you collaborate with your friends, as you cite your friend, you give impact and get impact from your peers. This is of course a very odd field, because now, especially now, it's very, very active because you see how quickly the number of applications in bibliometrics has grown just in the last 20 years by a factor of 10. Because now there are citation data databases which are available, even publicly available, so everybody can use them. For instance, we can easily get for free the APS database, including all papers published in journals of the American Physical Society since its inception, 1892 until today. So you can just make a request and you get this data. And we're using also this data to make things. So, but of course, if more and more people use it, there will be not so much to do for us. So keep it quiet. Start to download these things in a couple of years' time. Let me do some more stuff before that. So among the things that you may be interested in discovering is, or analyzing, is the activity of scientists, their citation patterns. It's very nice to see, for instance, also there are some groundbreaking events. The H-index is introduced. And then you see what happens after the H-index is introduced. The people form even more cliquish structure in which people asking friends, give me the citation, then discussing it before the experts. So that I can have an increase on my H-index by 1, 2, and so on. So also these things can change. And of course people get adapted, because once they know what is the cost function, it's again clear, it's like in the stock market. Then they change a little bit their habits in order to get as much possible profit out of what they do and what their peers, their colleagues are doing. And of course, last thing is evaluation of scientific output. Which measures shall we use for a more objective, whatever that means, quantitative evaluation of the impact of people, of scientists? So, very in question, of course, the bibliometricians and psychometricians are studying this all the time, much longer than us. What we can do is to have the global perspective, the statistical point of view of studying large systems that they usually don't consider. They usually focus, of course, also on large systems, but in very simple statistical signatures, correlations, and so on. We can do more in this respect. And I will show you what we did in there. So first of all, community detection. This is a very old problem, older than me. So if you think that I'm old, this is a very old problem. End of the 60s, the very first data sets were set together and people wanted to find groups. Like these three groups here, red, yellow, and blue. There are theoretical reasons to study this problem. Why should I find groups or nodes which have something in common? Because I want to know, I can find out how the system is organized. Take, for instance, the human body. There are cells everywhere. Some of them are specialized, and they form the heart, the lungs, the liver, the brain. These are still cells, a different type, and of course they will stay together. They are specialized because they have a specific function. And they are similar, and therefore stay together. Or you can also classify a node based on a position in its community. If the guy is central in his community, that is in contact with many people, or if he's in the border between communities, acting as a kind of intermediate between different groups and different parts of the network. So if it has a function in terms of communication and diffusion process, or if it's kind of more a central hub which is kind of controlling everything. If you know what the communities are, then you can make this additional classification. If you don't know, of course you cannot. You can see things only from the global perspective. Or the very local one, or the single node and its neighbors. Visualization. I showed you, of course, this is what? 4 plus 5 plus 6, 15 nodes. But there are people now handling a system with 1 billion nodes. It would be more difficult to visualize than this, right? In fact, it would be even meaningless. Because, first of all, there are no programs able to do that. And then, what kind of information can you get if you put all these tiny points? It's impossible, it's a big mess. But if you know how it is organized in terms of communities, you can try to represent the system through its communities instead. So you make a point is a community, including already many nodes, which can be thousands or 10,000. Then you can get the first impression, okay, this is a basic organization, like the organs of the human body. Instead of seeing all the cells, if You see all the cells, you don't really probably learn so much. Then you see, okay, this is the liver. Let's see what's inside the liver. Then there are tissues. Then you can see. So these kind of hierarchical visions from the top to the bottom. These are good theoretical reasons. There could be others. Practical reasons, which are the reasons, the main motivations why computer scientists are interested in this problem, is if I know what communities are, I can implement very efficient recommendation systems. Suppose to take a bipartite network, which means the network divided into two classes of nodes, in which there are links only between nodes of one class and nodes of the other one. It could be people, customers, and Amazon products. People buy books, DVDs, food through Amazon. Identifying communities of customers and products can give them the indication, and usually they use similar things, not really based on clustering, but recommendation systems are often based on clustering, on the clusters, saying that if I'm in the same cluster of guys buying, I don't know, Barilla pasta, then I may be interested in buying Barilla pasta one day. So I say, okay, I bought tomatoes, and then Amazon say, why don't you buy Barilla pasta? Because I know there are people similar to you who bought it very often. Another reason is very important, especially in biology, is identifying unknown protein functions. But you could apply to also other properties of different systems. Say that I have a cluster of proteins in protein-protein interaction networks in which the nodes are proteins and the link between the protein is there if the two proteins are involved in at least one common process. Suppose that I know, because I make experiments as a biologist, a rare biologist, to find the function of a group of proteins, but I don't know the functions of others because perhaps the experiment is very difficult, it's very expensive, and I cannot afford it. But if I find the clusters in this system and I know the functions of many proteins in the same group and I see that this function is the same, then I can say, okay, so maybe the function of these other proteins in the cluster, which is yet unknown and identified, is probably similar to the function of these other proteins in the same cluster. And that can orient and guide my future experiments. That means saving time and money. And I can give you many other examples like this. But just to tell you that this thing is not just a game, right? And just to get into some kind of striking representation of this, this is the problem. It's a very difficult problem because what you have to do, what I have, the only information I have is I know which nodes are connected to which other nodes. So this is represented by the so-called adjacency matrix. You see I have 50 nodes. The entries 1 indicate that in this case node 3 is connected to node 1, or node 4, okay, this is probably wrong, it should be 5 or something. Cannot be connected to itself because usually we tend to discard self loops. All the white space indicates zeros, means that there are no links between the corresponding nodes. So I'm given a matrix like this. You see this, you don't see any order. But this is the same system. This is this matrix representing this system here. So if I show you this picture, you see there is order. There are groups on nodes which are many links together. So community detection means transforming this matrix, exchanging the orders of the nodes, reordering the nodes so that at the end you identify the groups. So you see now this was 1, 2, 3 and so on, the order from 1 to 15 because I didn't have any information. But the nodes 6, 2, 8, and 14 are these 4 red nodes, and the same for the blue nodes here, and the same for the yellow nodes. So if you rearrange the matrix properly, and there are clusters, then the matrix will look like this, block diagonal, showing that there are many links connecting only, mostly, the nodes of that group, and very few between groups. For instance, these two things are nodes connecting, in this case, this one, actually both because the matrix is symmetric, yellow and blue, one of these two. And this is the other one. Okay, so this is in principle what any clustering algorithm should do. Transform the adjacency matrix to bring it in block diagonal. If you put it to a form like this, then I know this is a group, this is a group, this is a group. So imagine to do this for a system with 1 million nodes or 10 million nodes. This already looks quite messy. So imagine how messy a much larger matrix like this will look. And this is a very simple case in which there are very few connections between groups. Usually there are many more connections between groups. There is much more noise. And even the number of solutions that you can have by reordering the matrices the way I did it now is very high and difficult to navigate. So this is in principle what I want to do. I want to start from here and get to here. It can be done in many ways. One of the most popular ways, and most probably still the most popular way, is modularity optimization. The optimization of a function which tells you how good a partition is. So this was introduced by Newman and Geber in a paper 2004, originally used to say how good partitions delivered with other techniques were, and then it became a method on its own. This is modularity. It's indicated with the letter Q, and is the total number of links of the network. So how many person nodes are connected. This is the sum over all the clusters. In the previous case, there were 3 clusters, red, yellow, and blue. And for each cluster, I have to compute this difference. LC is the number of links connecting nodes of the same color. Okay? The green nodes, actually there are not green nodes, so the red nodes, the yellow nodes, and the blue nodes in the previous example. Minus this expression here, where DC, M is still M, the total number of links of the system, of the whole network, and DC is the total degree of the nodes of community C, meaning the sum of the number of neighbors of each node of the same color. So how many neighbors all the yellow nodes have, all the blue nodes have, all the red nodes have. And this is the way. The idea of this measure is to show how different each cluster is from a subgraph of a cluster which has very similar properties as the original system that you're considering, but it's otherwise random. The idea is that the existence of communities, the fact that there are densities, high densities of links within groups, means that there is some sort of order, some sort of correlation. You don't have these kind of things in a random graph. Because random graph, basically everybody can be attached to anybody else. So we are all at the same level. I can pick you or you and so on. Whereas community detection means that I like you better, so I send most of my links to you. So this is a different situation. And modularity measures how far you are, how far a partition is from a partition of a similar system which has some properties in common with the original one, but is otherwise random. This will be more clear in the next slides. So this system that I used to compare myself, to compare the original network that I'm studying, is a null model. Can be defined in many ways, but modularity null model, the ones that gives you the formula that I showed you before, is a so-called configuration model, introduced already in 1995 by Moller and Reed, which are mathematicians. So random graphs, so there are random graphs which have the same degree sequence of the original graph. So I take the original graph, like this one. This is my original graph. I see there are 3 communities. Okay? And modularity would count, so if you compute the modularity of this partition, then you have to make the difference of those 2 numbers that I showed you for this one, and for this one. Okay? But this is the original graph. So here there is order, because you see, there are communities, there are big densities of links inside the groups. The configuration model basically says the following. So each node, I can show you again, each node basically, you see this guy here has 3 neighbors, which are 3 other yellow nodes. In the configuration model, this guy still has 3 neighbors. You see there are 3 so-called stubs coming out of the node, but he can choose to attach these stubs to anybody else. Okay, this is the randomness. So it is a system which has the same number of nodes, the same number of links of the original one, and each node has the same number of neighbors, but I can decide to rearrange this as I wish, in absolutely random way. A system like this would somehow destroy the communities, because obviously now the green node, the yellow here, will be very likely attached to a red one, because there are many more. And I pick them with the same probability. I pick each stub with the same probability. Okay? Until all the stubs are connected, then I get a graph, and then of course I can repeat the procedure, and I get another graph, so this is a whole class of graphs, and I'm comparing the original system with this class of artificial graphs. So this is the configuration model, and this is the comparison term of modularity. Modularity optimization consists in finding the partition of the system. I give a network, there will be infinitely large number of partitions. The partition of the system which has the largest value of Q. There is always a partition with the largest value Q, because Q cannot be bigger than 1. To show you why this is so, but we don't have time if you are interested in that. So there is an upper limit, so there is always a maximum. It's usually non-trivial maximum. it is an NP-complete problem. This was shown fairly recently, 2007, by computer scientists. Okay, which means that unless you're very likely, it will take you an infinitely long amount of time to find the absolute maximum, even for small networks, because there is no simple way to do it. There is no polynomial way to do it. That is, until somebody shows that P and NP are equivalent, which is an often challenge in theoretical computer science and mathematics. So, it is an NP-complete problem. You cannot hope to solve it exactly to find the absolute maximum. You can find it in an approximate way. And people spend a lot of time, too much time in my opinion, to find approximative techniques to find this maximum modularity. Greedy algorithms, simulated annealing, extreme optimization, spectral optimization, other strategies including genetic algorithm and other things. There are many ways to find the maximum of this quantity in the set of all possible partitions. But what I tried to do was wondering about the significance of the maximum. Suppose that somebody tells you in your ear what is the maximum, the partition which gives you the largest value modularity. With the absolute maximum. There is no other partition with a larger value. What is the meaning of this? This is in this paper here, which was the first work, somehow critical work in community detection. Critical because it was some kind of somehow questioning about the principles. So let's take the examples that we had before. Let's see where the problem comes from. Because what we found is that there is a problem. There is a resolution problem. Modularity is not able to find small groups, even if they are well defined. Let's focus on the blue nodes that I call subgraph 1. It has degree K1. K1 is the sum of the neighbors, or the total neighbors of the blue nodes. So it's 4 plus 5 plus 3 plus 3. Oh, these two are still connected. I forgot to break this one. It was a small one. So this will be K1. The same thing I can do for the yellow one. And then I ask myself this precise question. What is the expected number of edges between yellow and blue in the null model of modularity, in the configuration model, if I can attach all the stubs at random? It's a cluster of networks, which means that each network will have its own result for this question. But I can wonder about the expectation value, the average of this number over all the configuration of the model. So this is very simple because I had to pick two of these half links that you see there at random. The probability to pick a blue stub is K1, the number of blue stubs, divided by the total number of stubs. Since there are m links, each link gives you two stubs, because if you break it, each link gives you two halves. Then the probability to pick a blue stub is K1 divided by 2m. The same thing to pick a yellow stub. So one of these one. There are K2, but there are altogether 2m stubs. The probability to pick a yellow stub will be K2 divided by 2m. Since I can do this in the two orders, first blue and then in the yellow and vice versa, there is a factor of 2. Okay? So this is the probability that if I pick two stubs at random, they will be connecting a blue node with a yellow node in the null model, when I can make connections this way. There are m links altogether. So if I multiply this probability by m, I get the expected value. So how many links I would expect to be between blue and yellow. So if you make this multiplication, you see this is K1 times K2 divided by 2m. Very simple. Question, very simple. So this is how many links I would expect to find between the two groups in the null model. In particular, if you are considering only blue or only green, you may wonder what is the expected number of links that I find connecting a blue node with another blue node. I just need to put K1 equal to K2. I do the same thing and I find that this is now what in the previous transparency when I introduced modularity I called DC. So this is where the term comes from. This was, if you remember the formula modularity, this was the term that I had to subtract. So what is this term? Is the expected number of edges between blue and blue, if you want, or yellow and yellow, red and red. So how many links I would expect to find on average in modularity scheme. So the idea of modularity is that I have, in the partition of my system, I have LC, this was the formula, LC links connecting red and red. I expect to have this. So if LC is much bigger than this, means that there are more links between reds or blue or yellow, then I would find the null model on average. Then I say, why is it possible to have a much higher density of links within red, or within blue, or within yellow? That means that these nodes are somehow more connected to each other than they are in a random system with the same properties. So this group is a community. This is the whole idea about modularity. So comparing what is the stuff that I find in a cluster, and what is the stuff that I expect to find inside the cluster in this new model, in which I can attach nodes at random. So the result is very simple at the end. I mean, of course, arriving there was not so simple, but this is just an argument. So this is the number of, expected number of links between blue and yellow. This number can be smaller than 1. If n is large enough with respect to k1 and k2, or if k1 and k2 are small enough, so if these two subgraphs are small enough. So in this case, it means that on average, in the null model of modularity, I would expect to find less than a link connecting blue and yellow. Which means that in many cases, in fact, of course, this is an average, of course, which means that in many cases, in the copies of the model, the configuration model, equivalent to my system, the two subgraphs will be disconnected. Okay. So if there is even a single link between blue and yellow in the original system, this single link means that these two clusters are very strongly correlated, even if it's a single link. Because in the null model, in many cases, these two pieces will be disconnected. And this is what I call the resolution limit of modularity. If k1 and k2 are of the same order, square root of 2n, this is going to happen, so this ratio is going to be smaller than 1. And these two pieces, which are connected in my original system, but still are they're connected by a single link, so are very, very loosely connected and still well defined, can be very strong communities, will be put together by modularity, systematically. Because it's okay, there is a correlation between these two pieces. I don't care what's inside, but in the null model, these two pieces will be disconnected. So if I find them connected, it means that they should stay together. And these are some of the consequences. If I take a system like this is a very simplification, where all the yellow circles represent complete graphs, which means graphs with n nodes each, which are all connected to each other. Okay, complete means this. So all the nodes are connected to each other. So this is a very strong community, because the density of links inside is the highest possible density. There are no zeros. So everybody is connected to everybody else. But still, if these pieces are small enough with respect to the rest of the system, modularity will not see them. It will put them together in groups of 2 or 3 and so on. Because of this, because in the null model, these pieces will be disconnected. So if they are disconnected, whereas here they are connected, you see there is a link between these two yellow green things and a link between these two and so on. These links indicate the modularity, there is a connection, there is a correlation between these two things, which is not random. And therefore we put them together. So this is a systematic problem of dimension. But the main question about this is, if I'm given a network that I never seen in my life before, so I have the adjacency matrix, I apply modularity optimization. I find the absolute maximum modularity. So if this is a partition, gives me the highest value, it should be the best possible partition. And this is a cluster. This is a cluster with total degree smaller or the same order of square root of n, where n is the number of links. I don't know a priori if this subgraph looks like this, so it's a real community, connected, compact, or like this. It's made of pieces which are loosely connected to each other. I don't know it a priori, because in both cases modularity will put everything together, for the reasons that I told you. Because it will consider this single link here as a strong sign of correlation between these two subgraphs. So it's a very important, somehow, principal problems. How to make sure that you are taking the good ones and they are not overlooking at the smaller structures. And there are ways recently introduced to try to solve this, but then we found other problems and other people find other problems. In general, I would say it's better not to use modularity to find community singles. Now, it was good a few years ago, it's not good anymore, especially if you take large systems. Because the larger the system, the easier this problem will be there. So the origin of the resolution limit is the fact that the null model says that every node can be attached to anybody else. This is not realistic, because that means basically that every node can see what's everywhere else in the system. Of course, it's a very simple assumption, it's the easiest possible one. But if I'm in a web, I'm just doing a web page and I try to make links to other web pages there, my opinion, my perception of the web is a very small system with respect to how big it is. It's more than 20 billion pages. So community structure is local. If you want the mesoscopic, I say fairly local system. The more so, the larger the network is. And considering any global null model, like the one on modularity, it's not a good idea. I can give you this promise that I told you. This was the main message of the paper. So, the idea is obvious. I mean, if I can combine any two stubs at random, so blue can pick a yellow or a red with the same probability. Suppose that I make this ball 10 times or 100 times bigger. Then blue will always be connected to red. It's very, very unlikely that it will be connected to yellow, because these two pieces are very small. So in the null model of modularity, basically these two pieces are always disconnected. So even if they are ideal communities, if all the yellow nodes are connected to each other and all the blue nodes are connected to each other, modularity doesn't care. They say, okay, there should be links, there should be no links between them. So if there is even a single link, it means that they are connected, they are correlated. So this is a problem that trigger a number of things, so-called multi-resolution methods and so on. Our solution to that, community detection is a local phenomenon, so let's use local methods. Last week, like I was saying to the experts this morning, we just published this paper, a paper introducing this method, Oslom, which is based on optimization, but it's a local optimization of a fitness function. If you go to the website www.oslom.org, you can download the code and can use it to analyze any graph that you like. There is a Whitney file, you can use it for directed networks, for weighted networks, for anything that you want to do. If you have problems, you can write to Jose, who is one of the guys in charge. And it's usually his fault, of course, the thing doesn't work, so you can blame the right people at least. Actually, it was my PhD student who did most of the work. So, go local. Take-home message. Modularity is unreliable. Global null model, resolution limit. So let's go local. Let's look at what happens in portions of the system. The other thing that I tried to do, again, to upset people, was the problem of testing. You propose a method, you have to convince me that this method is good. How to do that? This question is, in my opinion, even more important than finding a method, because it means what you're supposed to find, what your method is supposed to find, what kind of system or groups are supposed to find. So testing a method means applying it to a system in which you know the answer. If the method finds the answer, it's good. If it doesn't find the answer, it's bad. Okay? That's what testing means. There must be a ground truth. Problem is, there is no ground truth in community detection. That's why every day you see at least one paper with a new method. Because everybody says, okay, I would like to study this data set. I invent a method, more or less connected to previous ones or completely new. It's much more difficult now to find new methods because everybody has made things of this kind. And then, if I find reasonable answer, this is good. So in this way, you can proliferate methods for ages, which is basically what happened. When somebody asked me about the progress of this field, I said that basically it's moving in a circle. So you have the impression that you're going ahead, but you are at the same distance from where you're supposed to be from the center of the point, just because people are doing this. So if we agree on a set of systems of graphs in which most methods, if not all methods, should find the groups that you put with your hands, then we make a progress, because it means that at the end we have a benchmark which is common to everybody. So anybody proposes a new method, applies it on this graphs. If you find the clusters, it's good. If it doesn't find the clusters, it's bad. Very simple. So that's why, some years ago, we proposed a benchmark, which is now called LFR benchmark, starting from something that people were using anyhow, which was introduced by Condon and Karp in 1999. These are two computer scientists, and it's called the planted L-partition model. It works like this. I have n nodes, like in this case, which are divided in 5 groups, indicated by the big balls. The groups have the same size. There is the same number of nodes in each group. And each node has the same number of neighbors. So it's very completely symmetric thing, very unrealistic. In fact, that's what we did. There are two parameters. There is a probability P that two nodes in the same group are connected, and a probability Q that two nodes in different groups are connected. The idea is, if the probability that two nodes of the same group are connected is larger than the probability that two nodes in different groups are connected, these groups are communities. Very simple. It means basically it's more probable to link two guys with the same color than guys with different color. That was the original idea. And what we did in this paper, which also is another version, another update for networks with directions, weights, and overlapping communities, is to make this model, which is very simple, more realistic. I mean, all the degrees are the same in the planetary partition model. So we didn't make this. We made them heterogeneous, power law distribution of degrees, just like like in the web, like in so-called complex networks. No? That there are few nodes which have many connections, and many nodes which have very few connections. So you introduce a parameter which is the exponent of the power law, and you see this is a visualization of this. You don't know how clear it is. Some nodes have many more neighbors than others. The clusters have different sizes, because this is also known that in real systems there are small clusters and large clusters, where in the original model all the clusters are the same. And then there is a mixing parameter which tells you basically the ratio between the two probabilities P and Q. Okay, it tells you how many links I have outside of with respect to the total number of links. So 50% means that half of my neighbors are of different colors, half of the other half of neighbors are of the same color.
And the three different parameters are independent?
Yes.
You can fix two and just move the new.
Right, exactly. This is what people do. I mean, you fix actually these two, but you are free of doing it. Then you tune the new, bringing the system from when the clusters are very tight and basically detached.
Multiple links are not allowed.
Well, no, they are not allowed. They are excluded, but I mean, they could be allowed, and it's not a big deal. Usually the system is large enough, these things are not big complications. So, so you can find all the software here, you can apply it, you can decide these two exponents, you can tune the MT, you get your cluster graph, you apply your method, and then you see if you find the partition that we put in the system or not. And this is something that we did as soon as we developed this software to see what is the best algorithm, because people are just picking algorithm at one. They don't really know why they're using an algorithm or the other one, because like I said, there is no way to assess their performance. So no way that everybody agrees upon. Some people are criticizing also this settlement. And some right, because of course they don't have other properties that real networks have. They are not triangles in our benchmarks, because nodes are attached at random, so it's very unlikely that if two nodes are connected, they're also connected together in another guy. But still, I mean, we try to make a progress to make these things closer to real systems. And it was enough to do that, to give problems to many methods. Modularity optimization fails miserably in this case. So if we had introduced this years before, it would have been clear, for a very long time, modularity optimization was not a good method to find communities, whereas there are still people using it today, and making also science papers with it. So, just to tell you how things can get out of hand. So I made an analysis, basically who picked some of the most known methods, those for which it was possible, either easy to write the code, or the people were giving us the code, or the code was freely available. These are some, the label of these methods, and these are the orders of the complexity, so how quick these methods are, how long it takes to get the result, in terms of how many nodes you have, and how many links you have. And the answer was this. That was 2 years ago. Huh? So by now we have our method, so try our method first, and so our method is as good as this one. At that time, of course, we didn't have it, so. Informal. You find it's freely available. It has a very low complexity, so it runs also for a very large system of millions of nodes. It runs also for directed networks, so if the adjacent semantics is asymmetric, if there are directions. So it's a good game in this case. What you do, so here you see some of our tests. These are the 12 methods that you see in the list before. For each method you have a panel. There is this mixing parameter UT that you were mentioning. Tells you when it's 0, tells you basically that there are no links outside the community. So the communities are very, very well identified, and every method will find it. That's why you see that the efficiency at recovering the partition is maximum, 1 for all methods when mu is low. But then you increase mu, you start to mix them more and more. At some point you mix them such that there are no communities anymore, because there are minimum links outside the groups and they are inside. And therefore, of course, all methods will fail, the performance goes down. Here you see 4 curves for each of these methods, because we consider two different sizes, 1,000, 5,000 nodes, and then two different types of community ranges, from the minimum to the maximum. Small communities S, big communities B. Small communities means communities between 10 and 50 nodes. Large communities B means communities between 20 and 100 nodes. So this is some of the things that you can do with that. You can do it for your own method. You download our code, you create the algorithm, the benchmark, the parameters that we use for this analysis are published, so they are available. But more than that, we are going to do this for you, because we're going to develop the NetCom Analyzer, which is going to be the first portal. This looks ugly. Now we have hired professional web graphics, very, very good. We have a new layout. In 1 month, this thing will be up and running. So this is going to be a portal for the analysis of community structure. So if you want to do it, take a biological data set or a social data set, so you just download it here. You choose the method that you like. You will find a number of indications about which methods do what are the problems of each method, and so on. You click a button and you get your community. You get even a visualization, so the figure to put in the paper. So it's really minimum effort, maximum efficiency. And if you have your own method, which is new, and you want to see how good it is, you can download our benchmark graphs, the ones that we use for the analysis you see in the previous one. Of course, we won't tell you the answer. You find the answer with your method. You give us in some format that we give you. And then we create the same diagrams that you've seen before, and you can see how good they are with respect to the other ones. And then there will be a forum. There will be also a repository, for papers. There will be discussion. I hope that this thing will bring the community a little closer together, so that we can make real progress.
But is there room for a better method? You go back to the results before.
Yes.
This method, the implement,
Yes.
is pretty good until there are no communities, right? You mentioned when you create
Pretty much. Yes.
So this is the method.
Yeah. Well,
How can you improve upon this?
I wouldn't say that. I mean, there are also, and could tell you a number of things that since we are discussing later on, I can give you more details about it. It's certainly better than anybody else. So that when I made this thing here, means that it's far better than the
But
other.
it finds all the communities until there are no communities.
The question is, are you sure that you know what is the new T after which there are no communities? Huh?
Like you told me.
If you believe the net, yeah, it's true. Because I told you that the probability of having internal connections should be higher than the probability of having external connections. Still, there is at least one paper that also involves Jose, in which they try to see how sharp this threshold is, because there is also noise. There is noise, and sometimes because of the noise, I mean, it's not 1/2. First of all, the threshold is not 1/2. Mu T, if the system is very large, it's very close to 1 actually. The critical mu T. It can be arbitrarily close to 1. The larger the system is, because then you have many more channels or connections, and therefore the probability can get all the way to 1 or to 0. So, but what is the real threshold is not clear, because there is fluctuations. So it's an open problem. That's why I say, so looking at these things, of course, the idea is that the farther to the right you go, the better you are. So Infomap does this, so from this analysis was a clear winner. And it's also very simple, it's also publicly available. There are other tests that we've done, which is not so good, but this is technical. If you want, we can talk about this, but it's probably not the right moment to do it. So I can tell you more about this. I'm sure it will be interesting because it's pretty much your kind of stuff. So wait for this. As soon as we have it ready, I'll send an email to everybody, so including you and so on, because my contacts here, to try to have you as contributors or as users. You can just analyze your systems, with any method, you can get visualizations and so on. This is going to happen soon. And this is one of these two papers that Jose mentioned. One of my two surveys in complex systems. This is community detection, published last year. Quite a big effort also because I was the only author. And now it's in the list of the top 25 hottest articles for Elsevier in physics and astronomy. It's going quite well because there was not article like this. People did not know really what to read. They were just reading papers. There was no real comprehensive subject. So at least it's being useful. Now this is the part that will annoy Maxi, so if you want to take a break, for 10 minutes and I'm done. So this is a part about social dynamics, so collective behavior. I told you that I will give you 2 examples about voting, elections, and citations. It's going to be very quick. Elections is a very good system for us, for everybody, I'll say, with a physics background, because it's a very large-scale social phenomenon with millions and millions of people going to vote the very first day, the very same day. 800 million Indians vote together. So it must be even probably visible from satellites, like the Chinese wall or something.
And they're always wrong.
Yeah. And you have a lot of data about this. There are many places, repositories, archives of the Ministry of Inner Affairs, I just found out that we also have this data for some countries, not specified, of course Spain. And we had some data, we collected data for Italy, for Poland, for Finland, for Germany, UK, Russia, France, and the US. And this is the paper where we made this analysis some years ago with Claudio Castellano from the University of Rome, La Sapienza. We focused on proportional elections with open lists, which means it's a system, you're probably not familiar with that because in Spain, or wherever you was here, the system is like the Italian one now, is proportional with, this is political elections. So I don't know administrative elections how it goes here, but I'm informed about the political system. Basically, the ranking of the candidates for each party is made by the secretary of the party, by some elite. So it tells you this number 1, number 2, number 3, and so on, and people can only vote for the party but not for the candidate. Proportional elections with open lists are the elections that Italy, for instance, used until 1992, since the Constitution, 1946. Now we're using this block system as well. It's still proportional, but it's with closed lists like yours. And in Poland and Finland, they are voting this way even today. It's kind of amazing. Poland, we're not even voting at all, like a few years ago for obvious reasons. It was not really a democracy. But now they pick the system, and they're still using the system. And in Finland, they always use the system. Why do we want to do that? We want to have a system in which people are able to make their choice. Say, I want you to represent me in the parliament. Not just a party. Because I don't rely on the big box, but I know this guy, I know he can represent me, he's a good guy, I like him, and I want to vote him. So we wanted to model the competition of candidates to the same party. And that's what we wanted to do, because in previous papers, this is by no means the first paper on election behavior by a physicist. The first paper was published in 1999. It's a 2-page paper published in Physical Review with one figure and 10 references about Brazilian elections. In that paper, basically, they were putting together in a histogram, they were computing the distribution of the number of votes of candidates in political elections in Brazil at the federal level and also at the local level, because Brazil is a federation, so there are also elections for the local parliament in each state. But they were putting all the parties together. So basically, there was no way to find out what was the influence of the party, because obviously, it's important to know which party you are running for. And if you're a member of a big party, usually you're going to get many more votes than if you are an independent candidate or belonging to a small faction, for obvious reasons. There are also these issues of the useful vote. Is it useful to vote for a guy that I like but is never been elected? Or is it more useful to cast my vote for somebody that I don't like as much, but he has better chances to be represented, to be promoted? So it's always. Whereas we want to do something different. We want to just to focus ourselves on the same party and model the competition of candidates of the same party. So the background is the same, everybody's in the same party, so they don't get, in principle, then of course they do, because everybody's closer or farther to the secretary, human dynamics to work. But at least, in principle, you can assume, it's a fair assumption to say that the party doesn't play any role in this case, because they are all from the same party. And what we wanted to study was the same thing, the histogram of how many candidates get how many votes. The problem I had, and we were discussing with Claudio about this, was that I was afraid that this thing would be too noisy. Because obviously, what we want to know, what you have, this information, is how many votes any candidate got. So this is what we have in the data. But the distribution depends also on other variables. 2 other variables, in principle, which is how many votes in total the party is getting in that territory, because the territory is divided, so the whole national, so the country is divided in territories, in districts. In each district, there are parties representing a list of candidates. And you vote, if you belong to the district for that party, for one or more of those candidates. This is how it works. So it's important to know how many votes the party is getting in total there, because of course V cannot be bigger than N. No? Obviously, not because.
So
if it is, in Italy, I think that the also actually because there are all strange things happening over the score and so on. But still, besides, this is not happening anymore because now we're not voting on the system, right? So we're voting like you without preferences for the candidate, so it doesn't matter. And of course, it depends also on how many people we are competing with. If you're alone, of course, you will get V is equal to N, obviously, only if you're alone. But if there are 2 people, it depends if you get more or less votes than the other guy. If there are 3 people, the more people, the more difficult it is for you to become visible. So I was afraid that this histogram would be a function of 3 variables. And the surprise was to find out that it's not true. That this thing is a function of a single variable. And I'll show you the path to that. It's very simple. First of all,
what about the variable that tells you how many people can be elected?
That depends on how strong the party is nationally.
But I mean, in a given place, you can have only, for instance, 3 members elected.
Yeah.
Then the distribution among the...
No, but you see, I don't get, you see, this analysis is done considering all candidates, winners and losers. So if there is a threshold, now of course, I understand that people, if they know that not many people can be elected and so on, they can think about this useful vote thing.
Just how many candidates can you mark at least?
Yeah, no, at least one, but it can be more.
But it makes a difference.
We all need this information. We didn't have a chance to know. I mean, just know, what's the guy talking? Oh, it's good, but it's true. But let me show what I found, then we can discuss about this. Because usually whenever I show this result, people are at least curious, let's say, if not really happy. So the first thing is to show that this function, this histogram, it's probability distribution, is a function only of 2 variables. So it doesn't depend on n and q separately, but it depends on the ratio between n and q. N divided by q is the average number of votes the candidates of the same party are getting in some specific district. I don't know, in Mallorca, in Palma de Mallorca. Okay, so it's on average. This is what the party of Zapatero is getting. The candidate of the party of Zapatero is getting. Of course, like I said, we don't vote this way, but this would be just not to illustrate this. To show that what counts is really this ratio, B0, and not n and q separately, we made this scaling test. We divided in the data sets, so we fixed a window of values for B0. Okay, of course you cannot fix a value of B0 because it's a real variable, you cannot really fix it to a value, right? So you have to choose a window. If you choose it too narrow, there would be very few candidates fitting there, and therefore the histogram will be a mess. You already see that there is some noise here. So you choose at least the order of magnitude of B0. That's why you have 100, 1,000, 10,000. So first you make this filter. You divide, you pick only the candidates whose B0s are in these windows. And then for each of these 3 subsets, you make a division to show if there is an influence on the total number of votes n or not. So bigger and smaller than some threshold, right? Bigger than 300,000, smaller than 300,000. So you make it to statistically independent samples. The idea is that if what counts is B0, for both subsamples you should get the same signal. You should get the same distribution. If you don't get the same distribution, it means that it's important also the value of n0 of n, and not only b. As you see, these 2 curves, violet and azure, cyan, coincide. The good approximation, because there is noise, there are a few hundred people in this thing, so you have to make a histogram of a few hundred points. And also green and blue coincide, and also black and red coincide. That shows that n doesn't really play a role once you fix it 0. That was the first surprise. Second surprise was that, in fact, there is not even a dependence on B0. If you make the histogram not of V, but of V divided by B0, which means B times P divided by n. So you take all the candidates. In fact, in this case, you fix the value of B0, again, which is a window, the order of magnitude, essentially. But you see that even if you fix B0, so it's very different, you see from 100 to 10,000, 2 orders of magnitude, and still, of course, there is noise, especially here at the tail, but you see that, on the beginning, but you see that on the tail, despite all the noise that there is, this histogram is fairly independent of this. So it's a matter of scale. You find the right variable in this case, and then everything collapses. In fact, the final surprise was this. And once you consider all points, all candidates, and you make the right scaling, you divide V times V by n is on B0, this curve is the same everywhere. It's the same in Italy, 1958 until 1987, but we have many more things. Just it doesn't look too good to put too many points in the same slide. Poland, 2005, Finland, 2003. So in a range of almost 50 years, from the black and white TV to the internet, so just to tell you how much also the campaign politics has changed. Before usually went to listen to the candidates on the square or the village, right? Now you can get an email. You don't even need to leave your office or your house to know that there is a candidate running for the election. Still, the curve is remarkably distinct, especially on the tail. The fit of this curve is a log normal, At least the one that you see here, the black one. For those who don't know, a log normal is this function here. It has two parameters, mu and sigma square. But in this specific case, so you see mu and sigma square, in this specific case, these two parameters are connected, are not independent. Because by construction, since I'm dividing b by the average with 0, the average of this log normal must be 1. Right? Because the average of v is v0. So divided by v0 is 1. So basically, I have to force the first momentum, actually, yes, not actually the average, so it's 0. Sorry, yeah, the first momentum is 1. If I do that, there is a relationship between mu and sigma square. In fact, sigma square is exactly minus twice mu. And you see that this thing is consistent because 0.9 is minus twice 0.45. But still, there is one parameter which is free. So why should it be the same in Poland, in Finland, in Italy, in 50 years than in Spain? I leave the question to you. And then, of course, you know, seems not to be such a trivial thing. There was a nice feature by Mark Buchanan, the natural pattern behind our codes on the new scientist. A spin-off of this, and this is the last thing I'm going to tell you, is for citations. Instead of considering votes, voting a candidate, citing a paper or citing a person. Okay? This thing that I was saying at the beginning, scientometrics, science of science. These are 5 citation distributions for journals published, for papers published in journals belonging to 5 different categories according to ISI Web of Science. ISI Web of Science divides science in 172 categories, from acoustics to zoology. You may believe or not how good these categories are. It's not clear how they do it. Everything is secret and so on. But still, you know, we stick to this categorization. So we picked papers published in 1999. So all these papers were published in the same year. And of course, there will be disciplines with many journals and disciplines with not so many journals, but we downloaded all of them for that year. And you see how many papers get how many citations. Of course, the distribution is broad, because there will be some papers which are very well known, hundreds of thousands of citations, and most papers which will be uncited, almost uncited. You know, that's the case. No? We don't.
So this is the number of citations in each paper?
Yes, for each paper. In a discipline. So published in a journal belonging to one of these 5 categories. Same color means the same discipline. Right? Okay? So you see, we wanted to find again scaling and nice data collapse. Of course, here we get scaling, here we get a nice data collapse. Sorry. But the reason is obvious, and we should know that. C0 is the same thing like this B0 that you see in elections. So this paper was just basically a transposition of the same type of analysis to citations instead of elections. C0 tells you what is on average the number of citations that in 2008, when we did a study, a paper published in 1999 on average got in this discipline, in each discipline. So you see that aerospace engineering got the number close to 6. So after, from 1999 to 2008, so after 9 years, these papers got on average 6 citations each. But hematology got almost 31, developmental biology is almost 40. And that's clear. You see also this orange thing here, because in this case, perhaps there should be enough journals. So you see that hematology, so they are the ones which are come out stretching further away. Whereas, of course, engineering aerospace dies very soon. It's very difficult to have a paper with more than 100 sites in this case, for this discipline. Because on average, the papers are not very, very well cited. It's nobody's fault. It's a small community, perhaps there are reasons why. So there is a clear dependence on the field, where the field for us is the ISI category. ISI is not ISI in Turin, where I'm from now. It's ISI Thomson, Reuters. Yeah. Okay? It would be nice if we could have so much power. No? We decide who will get the position or the money. It's important. I don't want to have this responsibility. But then we ask ourselves the same question. C0 is different, like it was before for voters. Can it be that if we normalize the number of citations by C0, we get something more stable, more uniform? This is the answer. Some of the curves are the same that you see before, for the same label. There are many more disciplines here. So there's allergy, anesthesiology, and mathematics, neuroimaging, and so on. If you divide C by C0 and you make a histogram, the probability distribution of this number across all papers for this discipline, you see an amazing data collapse. So it's the same old game. If you compare yourself with the average, so if you want an analysis of the objective performance of people, performance means comparing how good you are with respect to the average in your peers. This thing is going to be the same. It's the same in voting, it's the same in citations. At least, this is what it's showing.
Sorry,
No, pardon is good,
I mean, this distribution should be stretched exponential or an exponential with a fat tail.
It is, yes. Well, it's a log normal. This plot is a log normal. You see in fact it ends here. But we found a better fit with a shifted power law. So variable plus a constant with some power.
No, because it says if, like Redner said, that it is a stretch exponential.
No, he said it's a log normal. But okay.
All right.
Yeah.
The C0, which you normalize it, is the average, and of course is the only parameter of the distribution, and comes out with that.
Yeah. If assuming the distribution is the same.
Yeah.
Is there a reason why it should be the same, like in biology?
No.
Yeah, so you said the result is still like this. So yes, I agree with you. So the fact that it's so regular means that there is something simple, something which is the same everywhere, something which should be not so difficult to grasp. It could be what you say. It could be something else. Still, doesn't change the result. The other question could be, and this is the last thing I'm going to show you. So this is actually what we think is the shape of this distribution, in the sense that I'm just writing a paper as we speak, actually, these days, in which we made the same analysis for APS journals. I told you that the APS data set is freely available. Now everybody can ask for it, they can get it for free. At the time we paid for it, it was $200, so it's a big thing. So we're doing something more precise with Complejos, statistics, just to make sure. Also, this is a huge database, the one I started to science. If you want to buy this, you have to spend a lot of money. We try to ask them for this data, they ask us, okay, we have 70,000 euros, and we can get it. Then they can make a specialized offering. You can get only science for the last 20 years, then you have to spend only 50,000. Also, because the last 20 years of science, there are many more papers than in the previous 100 years, or since Galileo did 20 years ago, because it's exponential. For some reason, people and nothing better to do than publishing papers on the area. So it's still exponentially growing, the number of publications in any field. So it's really amazing. The last thing I wanted to show you is that, like I said, we picked papers published in 1999. Somebody can wonder what happens if you pick a different year. If there is some sort of time, if you see that there is a time evolution of time dependency. This plot is showing it is not the case. This distribution has been stable. Somebody asked me for this today. I remember it was you and so on. It's been stable at least since 1990. It was difficult for us to make a very in-depth thing, considering also that some categories did not even exist 20 years ago, because there are disciplines which are new because they've been introduced now, like microbiology, for instance, or something like this. Or even neuroimaging, because you really need some devices and so on. But still, you see, 3 different years, 1990, 1999, 2004. Of course, the C0 changes because we measure the number of citations in 2008. So the farther you are from 2008, the farther you go back in the past, the longer is the C0, because there were more years to collect citations, obviously. So there is a pattern. And you see, in fact, 1990 it was 41 for hematology, 1999 it was 30, 2004 it was 15. But still, if you divide by the right C0, divide the paper in 1990 by 41, the paper in 1999 by 30, and so on, you see that there is no difference. Everything is very similar, at least in the last 20 years. You may wonder why. And then, now that you can compare them, is physics better than biology?
Yes.
It was Philip Ball. Yeah, of course, here. Yeah, it was Philip Ball. This is Nature News. So, see, citation statistics now comparable across disciplines. Many people are asking me now to get the magic number, C0s, to be able to say within a department if more money should go to the biology department rather than the physics, because they say they have more citations, which is true, whereas perhaps they should use this analysis to see if they're really so much better than their colleagues, not than their physics colleagues. Right? So it's better to compare you with people in your community, and this comparison apparently is field independent. This is the main result of this thing. And this is the other review paper that Jose was mentioning, which is now featured as a new hot paper in December. It's actually ISA Web of Science, so it includes all papers published in physics, and it can be downloaded from the webpage if you don't have the connection. These are acknowledgement to some of the guys involved in the stuff that you see in today's presentation. And with that, I finish. Thanks a lot. I saw it. Really, I should change the layout. Please.
I have a bit of a provocative question for the community detection.
Yes, sir.
I appreciate that certainly in the graph theory, the methods you introduce make sense. You're motivated at the same time, certainly from biological systems, from social interactions, where it's, for example, important to get a micro, meso, macro description of systems. But in your cases, the connections are only on or off, right? So usually
on and off, yes.
So you do not have the attributes that in real networks will always be there, which is certainly a coupling strength. It can be in social interactions that the connections are temporarily intermittent, that you might have transmission delays, whatsoever. So in how far is then this approach still a good approximation? Is there any information on it?
This is a very good question. I mean, like I said, of course, this was supposed to be a general introduction. We didn't want to spend some time on this. This is now a really independent field. It's been there for a long time. It's very active. And now, even this morning, there was another paper about it on the archive by Matthew Rosler, actually, the one of informatics. Another modification of his approach, since it's so nice, so it keeps changing its amount, improving it, just because it was encouraged by our analysis. We didn't know how good it was. So it was fine. Now that somebody else tells you how good the humanities is, you don't know when you publish the paper. All these things that you're saying are things that people are considering now, especially. The problem why in many cases you may not see traces of this, and also in some presentations of mine today, is the fact that the original problem, the way it is, just simple on-off connections on large systems and so on, is already terribly complicated. And there is nobody, if you ask like a random guy, even an expert, could be me or somebody else, but if you don't trust me, you can pick somebody else, I've used some of this before, can tell you, you should use this method, you should use this other method, this is better, and so on. Because they don't even know what is the criterion that they should use to say that the method is good. So until there is such an amount of entropy into this, such a big amount of disagreement in the community around a subset, at least of tools, they say, okay, let's use this one for this type of analysis because this is good. It's difficult to introduce additional complication. There are people who are doing it, and for instance, in this method we introduced, we have things called weighted networks, which means that is what you're saying, strength of the interaction. Links can be there in both cases, but one is 10 times stronger than the other one. So of course this thing should have an effect. On community dynamics, just again, it's something that you said, that the link can be there yesterday, it's not there today, it will be there tomorrow. So all these things are now being considered by somehow more advanced investigation. Of course, they know how important they are, just because of what you say. I mean, in general, what I tend to say is that the more information you have about the system, the better it is, you should use it. Whereas many methods are somehow conceived in a very naive way, and if you can use it for the standard version of the problem, you cannot easily adapt them when you introduce strength, the intermediate connections, even the edge direction. You can just take the method and throw it away, because it's not possible to generalize. And this is, in my opinion, a mistake. What we try to do with this is not just to increase by one, just to get to 1 million method, just because we're very close to this number anyway. I don't like this. I don't like
it. Might not even be trivial whether you have one strong connection or 4 weaker connections within the same community, or which are a factor of 4 small.
No, of course. No, I agree. So not only that, I mean, it depends also on the origin. I was speaking to the experts today. I was saying that one thing I will try to do in the next years is to try to make these things finally useful. Not because I haven't done it so far, but just because people should somehow try to specify their questions to specific classes of systems. Just because of all these things, I mean, for instance, in biological data sets, there could be an experiment saying that protein A and B are interacting, and the very same experiment done by another group in different conditions that say that A and B are not interacting. So, what shall I put a link between A and B or not? So there are things like errors, or uncertainty about whether a link is there or not. All things that are really there. You cannot just make an act of faith. Okay, I believe the first group and not the second one. You can try to see what happens if you do both things and see if there are any changes in the results. So all these things, all this information, all these symbols should come there. And this is what you can really hope to do if you really make a more contextualized analysis. You don't hope to, before, until a few years ago, but I would say even now there are people saying, we're just waiting for the final method, like the one-for-all thing. It starts from very simple ideas and finds communities everywhere. I don't believe in this anymore. I used to do it at the beginning. I think it's crap. So, and what I hope is to convince people that this is not really what people should do. Because it means throwing away useful information. If you have it, why should you? There are many things you don't know about the system. So, but if there are things that you know, why should you be able to use it? People say, okay, I apply my method to this system, even if it's weighted, I assume that the weights are equal. But this is a strong assumption. Or I analyze a piece of the web graph, in which 90% of the links are unidirectional, because there is a link between page A and page B, but usually there is no link coming backwards, taking you from B to A. The back button is not a link. For those of you who doesn't know, the back button is there is a cache memory that stores all your previous navigation. When you push the back button, it's like if you were writing the address of the page again on slot on the top of the browser. So that's not doesn't mean that the link is bidirectional. The link is what you find in the page, the thing that you can click in the page. And 90% of them are unidirectional. And many people say, okay, unfortunately my method is not good for direction. It cannot be adapted. So let's forget about direction and see what happens. That was good perhaps 3 years ago. It's not good anymore now. So I really hope to convince people somehow to make some progress, to do what you say, to bring these things in and not forget about them, but instead using them to find better results. So thanks for your questions. Anything else?
Thanks, Santo.
Thanks to you guys.
We'll be here until tomorrow afternoon, so if you want to talk to him.
Tomorrow I'm not sure, because perhaps it will take a stroll down generally, but later today if you want, friends as well, talk to me. I'm at the first floor next to the Thanks for your question.
Thanks a lot. No, it was not really meant criticism because I'm interested. But the point is really that also from our point,